this session. Okay, great. So today we'll continue with chapter 11. We're going to start a new section. This section will be 11.3, and it is about uh, this concept that I talked to you about yesterday, which is how can we start from a function and figure out if we have a power series for that function. And it turns out that we have developed already the tools we need to do that. Here's what I'm talking about. What we need to remember are Taylor polynomials, right? If you remember Taylor polynomials, we use these as the best polynomials we could create to approximate our function near a center A. So the center is important. We pick a center A, and then this was our generalization of the tangent line. So hold on a sec. All right, and this was the expression that we had for it. So we have the k derivative evaluated at the center divided by k factorial, that was the coefficient, and then times x minus a to the power k. And then the idea is, well, what if we don't stop at degree n, but we consider instead the power series we would get if we let n go all the way to infinity. And that's exactly what we're gonna call the Taylor polynomial. So Taylor polynomial, Taylor series, no polynomial. Taylor series is what we get when we consider infinity instead of n. All right, and I'll show a page from the book that explains this a little bit more clearly. So it's right here. So here is the description that we're talking about. So the Taylor, or also called Maclaurin. So we have also this name. We sometimes call them Taylor series. Sometimes we call them Maclaurin series. And the difference is we say Maclaurin when the center is 0. You have realized already that we use 0 a lot. It's one of those points that makes sense to have as a center many times. So when the center is 0, they have a special name, and that's because this guy Maclaurin studied them first, in particular when the center was 0. So James Taylor is the other one that is referred to here. And this is what it is. So it's just this series that we talked about. So it's the k derivative evaluated at a divided by k factorial times x minus a to the power k. And the difference is that we go from 0 to infinity. And then the important thing here is right here. So the important thing here is these two questions that are stated right here in the book. Question number 1. For which x's is this series convergent, right? Because if it's not convergent, then we just have a power series, but it's useless. When we plug a value of x, it diverges, so it gives us no information. So we have to know for which x's it is convergent. And the second is it gonna be the case that the Taylor series will actually equal the function? And that's even more important, right? Because not only will you have a Taylor series, which will be convergent, but maybe you know that Taylor series also equals the function, and then we have a different way to represent the function. So this second question, we're not going to be concerned about today. We'll talk about it mostly tomorrow, all right? So for now, we're gonna say it the way it is written right here in the book. So we're gonna talk about Taylor series and Maclaurin series of a particular function, but we're not gonna say it equals the function because we don't know that yet. In most cases, it will be equal to the function, but we want to justify it and say why. So right now, we're simply gonna say that we're gonna calculate the power series or the Maclaurin series of a specific function. All right? Questions so far? Okay, so let's take a look at the first question there. So let me show it again. So the first question here, the first example, right here. Example 1. It says we need to find the Maclaurin series. Remember, that's the one that is center 0. For these functions, part A, cosine x, part B, 1 over 1 minus x. So let's start doing that. Example 1. And we'll start with part A. So we need to write down the function. The function is cosine x. And then, just like we said, all we need to do is figure out the, so I'll write it here. What is, so we're calculating the Maclaurin series. So for the Maclaurin series, the center is 0. So this is what we need. The series from 0 to infinity, the kth derivative evaluated at 0 divided by k factorial times x to the power k. All right? Now, as usual, let's simply gather up the ingredients. What do we need here? We need the derivatives. The first, the second, the third, all of the derivatives, right? That's the difficult part of this way of figuring out power series, that you need to do the work. You need to figure out all of these derivatives, and that can be time consuming or downright difficult if you cannot figure out a pattern. But it won't be the case here. Let's do something we usually do when we need to do a lot of derivatives. Let's just come up with a table here. So we're gonna list over here k. And right here will be the k derivative. And right here, what happens when we plug 0. All right, and then remember, the 0th derivative is the original function. So we start with 0, and 0 is just cosine x. And what's cosine of 0? That is 1, right? Then first derivative, and that's going to be negative sign. And negative sign of 0 is 0. Second derivative will be negative cosine. So this will be negative cosine of 0, which is negative 1. And third derivative will be negative, not negative. The derivative of cosine is negative sign, but with this minus sign becomes sine x. So this is sine of 0, which is 0. And then we know what happens after this, right? So the fourth derivative becomes the same as, so the derivative of sine is cosine, so it becomes cyclic, right? So for k equals 4, so k equals 4 will be here, and 5, and 6, and 7, and then we go around, and then it's 8, 9, 10, and 11, and so on, right? So I think we got it. What is a pattern? Well, the coefficients, these numbers over here, are going to be, we start with 1, 1, then 0, then negative 1, then 0. And then again, 1, 0, negative 1, 0. 1, 0, negative 1, 0. Right? Let's write it down. So the first one will be 1. So it will be 1 over 0 factorial times x to the 0. That's 1. Then 0. So we don't write anything. Then the next one is negative 1. So it's negative. And now we're in the second derivative. So the second derivative is negative 1 divided by 2 factorial x squared. Then we go to the fourth, which is going to be positive 1. So it's 1, 4 factorial x to the fourth. Then the fifth one is 0, so we go to the sixth. So it's minus 1 over 6 factorial x to the sixth. And it continues on like that. Is that clear? So more precisely, this is what we get. So Maclaurin series is, like we said, 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial minus x to the 10 over 10 factorial, etc. Right? Now, how do we write this one in the sigma notation with the sigma, right? Notice that we go over the even numbers only and that it alternates signs. So the way to write it is as follows, is sigma, yes? So it will be negative 1 to the k, that's the part that alternates signs, x to the 2k, so that we go over the even numbers, and then divided by 2k factorial from 0 to infinity. All right. Is there a question?
Did Trump cause the Holocaust?
Is there a question here? Somebody's microphone is open. Just mute. All right. So, okay. So let's go back. We have this one over here. We're done. We figured out the Maclaurin series. The question now is, let's take a look at the first question. So where is this convergent? So where is this convergent? And we already practiced how to do this the last couple of sessions. So we need to find out the radius of convergence. And then once we get the radius of convergence, we then check the endpoints, right? So how do we get the radius of convergence? Our go-to tool is the ratio test, all right? So let's figure out the ratio test. So ratio test. How do we do it? Well, we need to calculate the limit when k goes to infinity, ak plus 1 over ak, everything in absolute value. What is this? This will be the, so I'm gonna do it like we have been doing it lately. So instead of putting the big quotient, 1 over the other, I'm gonna do 1 and then multiplied by the reciprocal of the other one. So this will be absolute value of negative 1 to the k plus 1, x to the 2 times k plus 1, be careful there, divided by 2 times k plus 1 factorial, times the reciprocal, so the same one, but written the reciprocal way. So it will be negative 1 to the k, x to the 2k, and 2k factorial, like that. All right? Now, from here, we can cancel the negative ones because the absolute value of negative 1 is 1. So we don't really need those negative ones. They will go away. And the factorials are positive. So let's, we can, this exponent over here, by the way, when you multiply it out, that's 2k plus 2. So I can simplify that this x to the 2k goes with the exponent 2k as well. All right, so what do we get? We get x squared 2k factorial divided by 2k plus 2 factorial. Notice that I removed the absolute value bars because everything here is positive. X squared is positive. It doesn't require absolute value bars. All right? Great. So all we need to do is do this limit. And to do that, we should simplify this quotient of factorials first. So let's do that. Need more paper here. All right. So let's expand that expression out. Okay, so this will look like the limit when k goes to infinity, x squared, and then what is 2k factorial? Well, 2k factorial is 1 times 2 times 3 times 4 all the way to 2k. And in the bottom, we have 2k plus 2 factorial, which is 1 times 2 times 3 times 4 times 5 times 2k times 2k plus 1 times 2k plus 2. It has 2 extra terms compared to the previous one. So a lot of the stuff cancels.
Professor.
These 2 terms in the bottom. All right? So now what we get is the limit when k goes to infinity of x squared divided by 2k plus 1 times 2k plus 2. And finally, we're ready to do this limit. What is this? What is the answer to this limit? Well, k goes to infinity, right? So k becomes a really, really big number. So this multiplication is big as well.
Is it 1/4?
Say that again.
No, never mind. I thought it was 1/4, but that's an x on the top, right?
X squared on top, yeah.
Oh, okay.
So, but it really doesn't matter what we have on top, right? We have some number, but we're dividing it by something gigantic, right?
It'll be 0.
So it will be 0. That's right. Thank you. So the answer is 0. And what were we doing this in the first place? The ratio test, right? So we should then compare to 1. So, well, 0 is less than 1, right? Therefore, when something is less than 1, that means it's convergent. And for what x's? Well, for every x, right? We don't have this limit turned out to be 0, no matter what x. So the answer is that the series is convergent for every x. So what is the interval of convergence? Well, then the interval of convergence will be everything, right? From negative infinity to infinity. So the interval of convergence negative infinity to infinity, everything. So that means the radius of convergence is infinity as well. All right. So then the latter question, the question we cannot answer at this point is this series over here actually equal cosine x? And that's the part we're going to be talking about tomorrow. In this particular case, it is. And that's awesome if you think about it. So we have a way of writing down an expression for cosine x as a power series. All right, but we'll talk about that tomorrow. All right, so let's move on to the next part. So part B. So for part B, we want to do example 1, part B. We want to do f of x equals 1 over 1 minus x. Again, Maclaurin series. So find the Maclaurin series. So I'll proceed the same as before. I'm going to write the formula right here. The k derivative at 0 divided by k factorial x to the power k. All right. Same instructions as before. We need to figure out the derivative, the first derivative, the second derivative, and so on. So let's do a table again. So here's k, and we're gonna do the k derivative, and we're gonna plug 0. All right, so the original function is 1 over 1 minus x, so this one is 1 over 1 minus x. I'm gonna write it like this, as 1 minus x to the power -1. All right? Then when we plug 0, we simply get 1 to the power -1, so that's just 1. Easy. Right? Moving on. First derivative. And that's why I wrote it like this, because this is a better way to figure out the derivative. I can take the -1 comes down, so it's minus 1 minus x to the power -2 times the derivative of the inner function, which is another -1. So this is just 1 minus x to the power -2. And when we plug 0, we get 1 to the power -2, which is also 1. All right? You with me so far? We need to come up with a pattern, right? This is the hard part. We need to do lots of derivatives. Second derivative, the -2 comes down. It's 1 minus x to the power -3 times the derivative of -x, which is -1. So it becomes 2, 1 minus x to the -3. And when we plug 0, we get 2 times 1 to the -3, which is 2. All right? Are you starting to get a feeling of what the pattern is here? Let's continue. Let's do a few more. Third derivative. -3 comes down, multiplies the 2, so it's -6. 1 minus x to the -4 times -1, so that's 6, 1 minus x to the -4. Right? And when we plug 0, we get 6. Right? And this 6 actually, let's think where this 6 came from. This 6 came from this 3 multiplying this 2. So it's actually 2 times 3, right? Let's do one more. And by this, I hope you see the pattern. So fourth one, it will be the -4 comes down, multiplies the 6, so that will be -24, 1 minus x to the -5 times -1, which becomes 24 times 1 minus x to the -5. And when I plug 0, I get 24. And more than 24, this is really 2 times 3 times 4, right? So have you gotten the pattern now? What is the pattern?
Would it be just a factorial?
Yes, that's exactly right. And it makes sense, right? So when we do the fifth derivative, this 5 is going to come down and multiply this 24. And 24 was 2 times 3 times 4. So now it will be 2 times 3 times 4 times 5, right? We're going to have an additional number there. So yes, so this is actually 4 factorial. This is 3 factorial, 2 factorial, 1 factorial, and this we can think as 0 factorial. Remember that we said 0 factorial is 1, so it makes sense. So in general, when we go all the way to k, we're gonna get over here k factorial. All right? Okay. So now let's backtrack, and so this was us collecting the ingredients. Now let's put them back into the formula over here, right? So this number we said is k factorial. So the Maclaurin series we need is the following, is from 0 to infinity k factorial over k factorial x to the k. And that's beautiful because these guys cancel. So our Taylor series, our Maclaurin series is just x to the k, right? Now, we kind of knew this already if you think about it, because we already know that the geometric series x to the k was convergent and that it equals 1 over 1 minus x. So we're sort of discovering in a different way how to get the power series of a particular function, right? We could have gotten this by knowing its geometric series. That's what we did before. Or we could have done what we just did right now and figured out that we get the same thing, right? Now, our previous knowledge here helps us out, because if I ask you where is this convergent, well, we have answered that question before. So we already know, we don't need to do the work again, that this series is convergent for -1 less than x less than 1, or absolute value of x less than 1, right? That's the interval of convergence. So no need for us to do that. And in fact, for this one, we know, for this particular one, we know, because it's the geometric series. For this series, we know that 1 over 1 minus x actually equals the series when the absolute value of x is less than 1. So we're fortunate to already know this for this particular series. All right? Questions so far? All right. Now, let's actually see another example, and this will also be illustrative of what happens. I mean, we cannot expect to get the same series if we change the center. So the center is very important. If you have the same function but with a different center, the power series, the Taylor series, the Maclaurin series, all of those may be different, right? Taylor series, I should say. If I say Maclaurin, is centered at 0. All right? So let's take a look at the corresponding page in the book. And so you can see what I'm talking about here. I think it's the next page or a few down. All right, so right here. All right. Okay, so here's example 2. The one we want to do now. So what happens if we do the same function? So you'll notice here, we're going to be using the same function, f of x equals 1 over 1 minus x. But now the center is going to be 5. So we want to find out what is the Taylor series and find the interval of convergence. All right? So let's do it. Example 2. So it's the same function, which is good because we need to find out the derivatives, and we've done that work already, right? There's no need to do it again. So let's show the work now. So it's the same function, but now the center is 5. All right? So let's figure out what is the Taylor series. So here is the formula for the Taylor series. We know it's just like the Taylor polynomial, but now we gotta plug it in 5. And it will be x minus 5 to the power k. All right? So what do we need? Well, we need the derivatives. We need, but we have calculated them already, right? If we take a look at our table from before, so let me recreate it here. So just write the kth entry. So we did a few, but really it's gonna be like this. So the kth derivative is going to look as follows. It's going to be k factorial 1 minus x to the power negative k plus 1. Right? Let me show you that that conforms to the pattern we had found before. Look at these ones here. So is 1 minus x to the negative 1, 1 minus x to the negative 2, 2, that's 2 factorial, times 1 minus x to the negative 3, 6 times 1 minus x to the negative 4, 24 times 1 minus x to the negative 5, right? So the pattern is the one that we were discussing. So it's these numbers over here are the factorials. So this is 4 factorial. And then it's 1 minus x to the power, the exponent 1 more, negative k plus 1. So just like we had here, right? So now let's plug 5. And when we do that, we get k factorial 1 minus 5 to the power negative k plus 1. All right? Good. So let's assemble our Taylor series. So here's our Taylor series. From 0 to infinity, this number, that's k factorial negative 4, that's 1 minus 5, to the power negative k plus 1, divided by k factorial x minus 5 to the power k, right? Again, we can simplify these k factorials, they go away, and we can put this negative exponent down. So this will look as follows. It will look like, well, the negative 1, it doesn't matter if it's on the top or on the bottom, so where you can leave it on top. And then is 4 to the power k plus 1, x minus 5 to the power k. All right, and that's as pretty as we can make it. All right, so that takes care of the first question. What is the Taylor series? Here it is, right? We figured it out. And again, the important point, the hard part of these problems is to come up with all the derivatives, right? If we have difficulty figuring out all the derivatives, then we're gonna hit a wall, right? That's gonna be an insurmountable obstacle. If you cannot figure out a way to get all the derivatives when you plug the center, then you're gonna be stuck. All right, so now when is this convergent, right? What is the interval of convergence? That's the next question. Okay, and same as all the problems, we're gonna do it by using the ratio test. All right, so here is again, our tool is the ratio test. We're going to do the limit when k goes to infinity, ak plus 1 over ak with an absolute value. That's negative 1 to the k plus 2, x minus 5 to the k plus 1, divided by 4 to the k plus 2 times, and then the same thing but flipped. So it's negative 1 to the k plus 1, x minus 5 to the k, and 4 to the k plus 1. Absolute value of that. All right. Next, these negative ones go away. We don't need them because the absolute value bar will take care of them. And then we can simplify this 4 to the k plus 1 with the k plus 2 exponent will become simply a 4, right? So we'll cancel this exponent and it will be just exponent 1. Similarly here, this x minus 5 to the k goes away with the exponent k. So all that is left is the following. an absolute value, an x minus 5 that survived on the top, and a single 4 that survived in the center, right? And same as other problems we have done, we lost the k. So when we do the limit, this is just a constant. So the answer to this limit is simply x minus 5 over 4. Notice that I don't have absolute value around 4 because 4 is a positive number. There's no need, right? And then ratio test. We ask ourselves, is this less than 1 to know it's convergent? And this is the same as x minus 5 less than 4. So that tells me the radius of convergence. So R is 4. So we can draw a picture here for when this function will be convergent. The center is 5. And we go 4 units this way. That would be 9. And we go 4 units this way. That would be 1. So we already know it's convergent inside, right here. And we still have the endpoints to check, right? So need to check the endpoints. So let's do it. Let's check the endpoints. So how do we check the endpoints? Well, one at a time, right? When x is 1, what happens when x is 1? Well, we need to go back to the expression. It's right here. This is the expression. So we have to plug the number 1. So we get from 0 to infinity, negative 1 to the k plus 1, 1 minus 5 to the power k, divided by 4 to the k plus 1. And what is this? Let's simplify it. Negative 1 to the k plus 1, negative 4 to the k, 4 to the k plus 1. We can again simplify further. Yeah, it's negative 1 to the k plus 1 times negative 1 to the k times 4 to the k divided by 4 to the k plus 1. Now this guy cancels with the k. And these negative ones, I can combine them, right? K and k plus 1 becomes 2k plus 1. Everything divided by 4. All right. And I can I already know it's going to be divergent because this is not getting close to 0, right? Now, you may be thinking that it alternates signs, but it actually doesn't because this is an odd number, right? What happens when you take negative 1 and you raise it to an odd power? Negative 1 to the 1, that's negative 1. Negative 1 to the third, that's negative 1. They're all negative ones. So this is actually just negative 1 over 4, which is obviously divergent, right? It's like negative 1/4, negative 1/4, negative 1/4, negative 1/4, etc. So divergent by divergence test. All right. Questions? Let's take a look at the other one. When x is 9. When x is 9, here's the expression in case you've forgotten, right? We just gotta plug 9 instead of x. So from 0 to infinity, negative 1 to the k plus 1, and this will be 9 minus 5 to the power k over 4 to the k plus 1. And what is this one? This is negative 1 to the power k plus 1, 4 to the power k divided by 4 to the k plus 1. This is easier to simplify. Over 4. All right. And that's as best as I can do. And so this one is This one does alternate signs. It's 1/4 minus 1/4, 1/4 minus 1/4, 1/4 minus 1/4, etc. So what is the situation with that? Well, it diverges too. So also diverges because the limit of -1 to the k plus 1 over 4 does not exist, right? It goes 1/4, -1/4, 1/4, -1/4, so it doesn't exist, all right? So then what is the interval of convergence of this series is 1 to 9, open on both sides, right? So these are the x's that are strictly between 1 and 9. All right. Questions?
Oh, Professor?
Yes.
So when you're finding the radius, how come you don't add the 5 on both sides?
The 5 is the center, right? Let me go back to my drawing. So let me share my paper. Right here in the center. So you start with the center 5 right here. That's the center. And around 5, so look at what it says over here. It says x minus 5 in absolute value less than 4. So those are the x's that are less than 4 units away from 5, right? So when you do x minus 5, that's like the distance, right? So if I ask you how far is 7 from 5, what do? You do 7 minus 5. And you say, oh, they're 2 units apart. But you could have done it the other way around too. You could have done 5 minus 7. It gives you -2. But if you put absolute value, the answer is still 2. So they're 2 units apart. So you can read this as these are the x's that are 4 units apart or less from 5. So that's what you do. You start from 5 and you go 4 units this way. That's how you find the right endpoint. And you go 4 units the other way. That's how you find the left endpoint. So from 1 to 9. All right? Is that clear?
Yeah.
Excellent. Any other questions? Okay, let's see what's next after this. We have another example. Okay, so let's get to the next example. So it's all about practice. So it's if you see, the good thing about this is we're not only practicing this new concept, which are the Taylor and the Maclaurin series, but in the process we're also still calculating the radius of convergence and the interval of convergence. That still matters. All right. So let's do the next example. So next example. So sometimes the examples are like this one here. This example number 3, if you see, they're not asking us to get the entire Taylor series. That may be too difficult at this point. Maybe we don't know how to get it. So sometimes the problems are like this, where it says, get the first 4 non-zero terms. So we don't want the entire series. We only want the first 4 terms that are non-zero. All right, so that presumably will make it a little bit easier. So let's do that one. So that's example 3. Our function is cubic root. So cubic root of x, that's the same as x to the power 1/3. And our center is 8. All right, let's go to the page. All right, so this This is the function and the center. And so here is the Taylor series formula. As you remember, it's just like the Taylor polynomial. So it's the kth derivative at 8 divided by k factorial x minus 8 to the power k from 0 to infinity. But remember, they're not asking us to get the entire thing. We only want the first 3, or was it 4? The first 4 non-zero terms. So the first of these terms that are non-zero. All right, so we presumably only need to get a few derivatives. So let's get that work in. So here's the k 0 derivative is just the original function. So that's x to the 1/3. And then when we plug 0, I mean 8, not 0, 8, right? We're doing it around 8. When we plug 8, we get 8 to the 1/3. And that's 2. All right, so that's the first one. Good, we have 1. So that's the first non-zero term. Moving on, first derivative, 1. So the first derivative is 1/3 x to the 1/3 minus 1. That's negative 2/3, right? In other words, 1 over 3 x to the 2/3. And when we plug 8, we get 1 over 3 times 8 to the 2/3. And 8 to the 2/3, 8 to the 1/3 is 2, 2 squared is 4, so this is 1 over 3 times 4, or 1/12. And we're in great shape. We have 2 non-zero. All right, keep going. Second derivative. Negative 2 terms comes down, so now it's 2/9 x to the negative 2/3 minus another unit, that would be negative 5/3. So that's the same as 2 over 9x to the 5/3. And when we plug 8, we get 2 over 9 times 8 to the 5/3. That's 8 to the 1/3 is 2, 2 to the 5th is 32. So this is 1 over 16 times 9. That's 144. All right. Great. One more. We only need one more. So we already have 3 that are non-zero. So it seems like we're only going to need the third derivative to go as far as that. Negative 5/3 comes down. So this will be negative 10 over 27 x to the negative 8/3. So that's negative 10. Am I missing a negative sign somewhere? I think I am. Let's see.
Yeah. When you brought the
One,
2/3 down, it should have been negative.
Yeah, negative 2/3 comes down. So this should be minus. Thank you, Michael. So it should be minus here, minus, minus, minus. And okay, going. So then this one will now be plus, right? So it will be 10 27ths, 8 to the 8/3. And when we plug 8, that's 10 27, 8 to the 8/3. So that's 10 27. And 8 to the 1/3 is 2, 2 to the 8. Right? So this is 5 over 27 times 2 to the 7. Or 5 times 27 times 128. Right? You know, you can leave it indicated. You don't need to do the arithmetic operations. It's perfectly fine to leave it like this, right? As long as it is a number, right? So now let's write down the first few terms of the Taylor series right here. So the first term is just 2. The next term is 1/12 is the number. 1 factorial x minus 8. The next is negative 144. over 2 factorial x minus 8 to the second power. And the last that we need to calculate is 5 over 27 times 128 over 3 factorial x minus 8 to the cube. And then it continues, right? It keeps going, but I mean, we don't know because we only calculated 3. It seems like a lot of work if we keep going, right? We don't see a pattern right away. So this seems like a difficult thing for us to do right now because not clear what the pattern is, right? But if they only ask for the first 4, we got it. We're good, right? Questions? All right. Now, the fact that we can always follow this procedure almost like a recipe, right? Like there's a function, we do the derivatives, we keep doing our table, we plug the numbers. The fact that we can do it like that doesn't mean we should do it like that. And this next example shows precisely what I'm talking about here. So let me show the next example to you. As probably the last one we'll do today. So this will be example 4. I think it's on the next page here. Okay, so right here, example 4. So this time we want to do e to the x. All right, and you're already thinking, oh, e to the x, that's great, because taking the derivatives of e to the x is actually quite easy. That's an easy thing to do, right? So you won't be wrong about that. But the interesting thing here is the last part. So part C is over here. So how can we use the information we're gonna learn from part A and part B to find out new power series, new Maclaurin series for x to the 4 times e to the x, for e to the negative 2x, and for e to the negative x squared, all right? So let's start first with figuring out e to the x. So Maclaurin series for f of x equals e to the x. All right. This is example 4. Okay, so all right, so as usual, we start by writing down the formula for the Maclaurin series. Here it is, from 0 to infinity, the k derivative at 0 divided by k factorial x to the k. All right, so it's real easy, right? Because what's going to happen here? Let's do our little table. So here's k, here's the k derivative, and here's when we plug 0. So we start with the original function, that's e to the x, and when we plug 0, we get 1, right? And then here's the thing, what's the first derivative? Well, e to the x, right? So we also get 1. What's the second derivative? E to the x. What's the third? E to the x, etc. All of them are e to the x. And so for all of them, you're going to get 1. So this is probably the best example they could have thrown at us, right? In terms of difficulty. Super easy. So what is the answer? The answer is 1. They're all 1, right? 1 over k factorial x to the k. We are done. So that's the Maclaurin series. Now let's find out the radius of convergence. And I believe that is part B. Well, part B is to find the interval of convergence. So we'll start with the radius of convergence. And for that, we use the ratio test. So ratio test is our go-to guy. So we do the limit when k goes to infinity, ak plus 1 over ak. And this will be let's see, is 1 over k plus 1 factorial, x to the k plus 1, put it right here on top, times x to the k factorial. Right away, this x to the k cancels with the exponent k, and we can expand the factorials to see what else is going on here. So we have absolute value of x, and then k factorial, which is 1 times 2 times 3, dot, 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 times k. And in the bottom, k plus 1 factorial, which is 1 times 2 times 3 times k times k plus 1, right? So all of these guys go away, and only this k plus 1 survives. And what we get is absolute value of x over k plus 1, where k goes to infinity. And similar to one we did for cosine early on, doesn't matter what x is, when you divide by something big, this limit will be 0, right? And because this limit is 0 for all values of x and 0 is less than 1, the conclusion is that this series converges for every x. Converges for every x. So R is infinity, and that means the interval of convergence is from negative infinity to infinity. All right, great. So we're done with part B. Now we can take a look at part C, which is the interesting one. So how would we do it if we wanted to do now power series for x to the 4 e to the x, e to the negative 2x, and also e to the negative x squared? Okay, and see that, and this is the part that I was trying to tell you about. So for this problem, there's the easy way and there's the hard way of doing it, right? The hard way would be to take these numbers and start doing the derivatives, because now they're not going to be as easy, right? If you do x to the 4 times e to the x, you're going to have the product rule, and the entire thing will become harder and harder. If you do e to the negative 2x, you're going to have the chain rule. So terms will start appearing, and it's going to be more complicated. The same for e to the negative x squared. First the chain rule, and then after that, product rule. So those derivatives will be difficult, really difficult. What is the better way? Well, the better way is to do it the way we were handling things yesterday. So we know that once we have a power series, we can combine it by substituting the values that we know, all right? So here we're gonna take a little bit of, I'm gonna assume, which we haven't done, we're gonna assume that we already know that this power series we figured out represents e to the x, and we're gonna verify that in all certainty tomorrow, all right? So by using that, the problems will be really easy. So this is what I'm telling you we're going to assume. We're going to assume that e to the y, notice that I changed it to y because my technique is going to be to substitute the value of y for things that we need. So the one we just calculated, this one represents e to the x, or e to the y in this case. So this expression is actually equal to, so 1 over k factorial y to the k from 0 to infinity. And this is true for every y, right? From negative infinity to infinity. So how can we get these ones then? Well, easy. For the first one, just take this one and multiply by x to the 4th, right? So make y equals x and multiply by x to the 4th. And what do you have? You have x to the 4 e to the x will be the same as x to the 4th times the power series for e to the x, which is x to the k over k factorial. And the only thing you need to do is put this x to the 40 inside. So this becomes x to the k plus 4 over k factorial from 0 to infinity. And if you don't like that it says k plus 4, you can do a j substitution where j is k plus 4. And then this becomes x to the j over j minus 4 factorial from 4 to infinity. And where is this convergent? Everywhere, because the original one was convergent everywhere. So this one is also convergent everywhere, right? We're done. We don't need to do the derivatives. We don't need to do the product rule. We don't need to do the ratio test to figure out where this one is convergent or not. We save ourselves all of that work by using the information from the previous one. Okay? Next, let's take care of the other ones. So for the next, if we want to do e to the negative 2x, how do we do it? Well, we're going to set y equals what? So easy, right? Well, what we need. So if it's the exponent is negative 2x, then set y to be negative 2x. And then we know that e to the negative 2x will be the series 1 over k factorial negative 2x to the power k. So this is going to be, if we simplify it a little bit, is negative 2 to the k over k factorial x to the k. And that's it. Same as before. Where is this convergent? Well, this one was convergent everywhere. So here, this one is also convergent everywhere. So for every x. So from negative infinity to infinity. This one works, right? And just to finish today's lecture, last one, when y is negative x, we do negative x squared if we want to do e to the negative x squared. So e to the negative x squared will be, here's the expression that where we're copying it from, will be the sum from 0 to infinity, 1 over k factorial, negative x squared to the power k. And when we simplify it, this will be negative 1 to the k over k factorial x to the 2k. And again, this will work for any x's because the original one has no restrictions. It's from negative infinity to infinity. All right? So piece of cake, right? To figure out what the new power series is and also to figure out whether it is convergent or divergent, right? We didn't have to do any additional work. All right, we're gonna be almost done here. Let me just make sure that you guys don't have any questions before we log out for the day. Any questions? Yes, you're supposed to put down your name for attendance. So answer on the chat and write down your name.
Professor, I have a question.
Yes, go ahead.
So when we found the Maclaurin series for e to the x, did we say that the function equals the series? Or
no, we have not justified that yet. We're gonna do that tomorrow. But assuming is the case, right? I know yes. So you are, and somebody is asking me to show the last slide. So I'm also gonna go back to putting it on the camera right here. Yes, so you'll notice, so you're asking, we calculated this Maclaurin series for e to the x, but I'm actually saying that they are equal to each other here, right? And yes, so we have not justified that yet. It is true, but we're gonna see it tomorrow. But let's use it. So right now we sort of use it, even though we don't know it, to learn how to do other ones that are related to e to the something. Mm-hmm. Does that answer your question, Michael?
yeah.
Okay. Also, remember that we're putting this, I'm actually uploading all of these sessions to YouTube, and I'm just putting links from our Canvas page, but you can also search them on YouTube and you'll find them. All right, so that in you want to review any part, you want to look it again, you want to use it to work on your homework, any of that, then you're welcome to do it. All right, if there are no more questions, I'll see you guys tomorrow. Thank you for your patience and for trying out, and we'll continue to making the best out of this situation. All right, see you guys tomorrow.